This is the Pearson Edexcel Core Pure Maths 2 paper from November 2021. Let's just go straight into it. I thought this was quite a hard paper though, to be honest. This first bit isn't too bad though. Z1 times Z2, the modulus of is just the multiplication of the two moduluses you got here. So this is just 3 root 2, right? So when you multiply two complex numbers, the mod just multiplies together, the modulus and the arguments add together. So of course when we multiply these two and do the argument, we're just going to add these arguments together. Except notice how this one is not in the correct r cos theta plus I sine theta form. It's got a minus thing here. So you actually need to swap this one. You need to put some negatives in the signs here, and that swaps this sign out, because of course you're allowed to put a negative in a cos and nothing happens because cos is even, so you're allowed to just replace this with a negative. You're not allowed to do that with sine. You have to also make the sign negative. But that's good in this case, right, because it swaps that sign to what we want. And so of course this actually has an argument of minus pi over 12. Now that's in the right form. We can add that argument to this argument, so it's pi over 3 plus minus pi over 12. And of course we just get this, which is that, and we'll have that. Good. Given that w is z1 times z2, okay, so we may as well do that. We've just worked out that when we multiply the two complex numbers, the moduluses multiply together, so that's going to be 3 root 2, and the arguments add, which we just worked out is this. So w is going to be this number here. Determine the smallest possible value of n given that the argument of w raised to some power of n is 0. Now for an argument to be 0, that means it needs to be 0 or 2 pi or 4 pi, right? It needs to have circled round and still be facing to the right over here along the positive x-axis. So I need that number there to become a 2 pi or a 4 pi or a 0, I guess, but I don't think I'm going to be able to make it a 0. When we raise a complex number up to a power, we can use some de Moivre's theorem here, right? So I'm going to raise this number up to a power n, which of course raises the modulus to the power and the rest of it here. But de Moivre's theorem says that this n can just go in here, so that's what that says. We can just put the n in there, and now of course we're looking for n pi over 4 to be either 0 or 2 pi or 4 pi or whatever. We can use n is 8 to achieve that, and that's the smallest thing. Lots of other bigger things would do it, but n is 8 is the smallest thing that would achieve that. Corresponding value of this, well, that's just 3 root 2 to the power 8, which I believe is 3 to the power 8 times root 2 to the power 8. Root 2 to the power 8 is just the same as 2 to the power 4. And we'll get this times this. You can do it in a calculator. Is that answer there? And we'll have this first question done. Good. Question number 2, I thought was a really harsh question for question 2 of a paper. So we need to take this matrix. We need to times it by, a line is y equals mx plus c, right? So if we times this by the vector x, mx plus c, we're looking to not necessarily be at the same point, but somewhere on that same line. So we get to a new x coordinate, which we can just call big X, and then we'll get to a new coordinate on that line, m big X plus c. So this is the situation that we need to kind of prove doesn't actually ever happen. So okay, well we can just multiply this out and we'll get this. That's the top row, that's 4 times this minus 2 times that equals that, and the bottom row would give you this. The first thing I maybe want to think about is, there's far too many variables here, right? So let's go over the x at least, the big X. Let's put in these ones into there and we get this. Now this doesn't look very helpful to start with, and I think this is why I think this question is quite harsh. You need to think that actually, this isn't so much an equality. Maybe I should have put an identity symbol here, because what this needs to be is this needs to be true for any value of x that you want here. Like anywhere on the line will go to anywhere else on the line is the theory that you're trying to say doesn't happen. So you're allowed this to be any x you want, which means that the x's, it's more like an identity. The x's over here must match the x's over here. So 5 plus 3m of them over here must be 4m minus 2m squared over here. And that finally gives us something that it looks like we can actually solve. Of course, we can rearrange this, and we can show via the discriminant that this doesn't have any roots at all. And so there's no m for which you can get from a line with gradient m to the same point on the line. So therefore, there are no invariant lines here. The plus c actually doesn't matter. You could have just done x, mx, big X, m big X, and then claimed that the mark scheme just accepts you writing down, oh, because I've shown that it's never the case for y equals mx, it's also never the case for y equals mx plus c, but it's probably safer just to do it like this. You can see the c's don't matter because at this point they just go away, like they were just irrelevant here. We just took the line from the x's. So yeah, that's kind of interesting. I think it's a really rough question to see, but just try and remember that trick. If you ever do see something like this in a real exam, try and remember that trick of comparing the x coefficients on one side to the other. Because if you're in an identity, those must be the case. We weren't solving for x here, were we? Because we were looking at a situation where this was just always true for any x on the line. So yeah, cool. Question number 3. We've got a function arc sine. Of course, the formula book has some things to say about Maclaurin series. which is this. It also has something to say about arcsine. When you differentiate arcsine, you get that. Of course, I'm interested in differentiating arcsine because the Maclaurin series tells me that that's what I need to do. So okay, f of 0 is clearly 0 because arcsine of 0 is 0, because sine of 0 is 0, so that's fine. Differentiate this via the formula book, which is this, and then we can put 0 into that, and we just get 1. So that's our first non-zero term. We'll have a 1x coming up here. Differentiate again. Now differentiate this. You could use quotient rule if you want. I never use quotient rule. I always just turn it into this and use a mixture of chain and product rule when I have to. So bring the minus half down, take away 1 from there, differentiate this, it becomes minus 2x, put it there. You can of course simplify that to that. Now when you put 0 into that, it of course goes away because of this x, so f dash dash is 0. So that term goes away. And what about the next term? Well, we have to use a product, of course, here. We've got x times this thing. So product rule says differentiate this one first and leave this one alone. That differentiates to 1, of course, so we just get this thing here. And then leave the x alone and differentiate this. Minus 3 over 2 comes down. I think I've actually forgotten the minus 3 over 2 here, looking at this. So that's my bad. The minus 3 over 2 should be here. And then you reduce it to a minus 5 over 2, and then you have that minus 2x coming up again. It's not going to matter, of course, and why I didn't spot that this was wrong, because when you put in 0, all of this bit goes away because of this x, and this 2x actually. And you're just left with this, which is just 1 minus 0 to this, which is just 1. So that's why I didn't spot that, but there should be a minus 3 over 2 there. And then, of course, we just use the Taylor's bit, f of x equals, well, this is nothing, this is x times 1, this is nothing, and then the next one is x cubed over 3 factorial times 1, and we just get this, and then we continue after that. Substitute x equals a half into the answer here to find an estimate for pi. So let's just double check actually how we're going to get an estimate for pi here. Well, f of a half is arcsine of a half. Now arcsine of a half is pi over 6 because sine of pi over 6 is a half. And that's not going to give me an estimate for pi unless I times everything by 6. So I think 6 f of the function of evaluated at half is going to give me pi, and therefore if I times this by 6 and then evaluate a half and chop these terms off, then I'm going to get an estimate for pi. So I think I need to do 6 lots of this approximated at a half here. We can sort this out, of course. 6 times is 3, I think. So that's good because it's 3 plus something small, which sounds a bit like it could be pi. This is 6, which cancels with that, which just gives you 1/8 here because 2 cubed is 8. And we'll get a decent but not great approximation for pi. Good, 25 over 8, you can verify, of course, that that is quite similar to pi-ish. Not very much, though. So, question number 4. Okay, use standard results. Well, here they are. We're not given a standard result for this. We need to know that this is n into n plus 1 over 2. Show that the sum of cubes for the first positive n odd numbers is this. Now, just be a bit careful here. It's very tempting to set up the sum from r equals 1 to n of 2r plus 1 cubed. But if you set up 2r plus 1, when you put in r as 1, you're going to get 2 times 1 is 1 plus, is 2, plus 1 is 3, and your first number will be 3 cubed, which isn't the first odd number, right? So that's why I've used a minus here. You could have used a plus here and then started at 0, but then my standard formula don't work so well, and I need to add in something into them as well. So I decided to do it like this, because that means the standard formula work. Of course, cube this out, using a bit of binomial, you get this. Separate this all out into the 4 bits, you get this. The textbook has this, the formula book has this, the formula book has that. You need to know that's n into n plus 1 over 2, and you need to know that that's just n. And this is looking promising. We need to factorize out an n squared, which I actually can't do right now, but I can factorize out an n from everything, so I'll do that first. I can also, this makes 2, this makes 2 as well, this makes 3, so that's all quite convenient, so we get this. Like I said, I can factorize an n at this point to make this. And then this looks like something I can just expand out. It doesn't look too painful. There are probably much more intelligent ways of doing this, but it's fine. What I'm really looking for is this minus 1, this 3, and this 2 to cancel, which they do, because that gives me another n to take out. And of course it matches, which is nice, so I haven't made a mistake. The sum of the cubes of 10 positive consecutive numbers, odd numbers, is this. Now, read this carefully like I just attempted to. This formula here works for the sum of the first n positive odd numbers from n is 1, 1 cubed plus 3 cubed and so on up to n cubed. This is not saying that. This is just the sum of some 10 random consecutive positive odds. So it could be 9 cubed plus 11 cubed plus 13 cubed and so on. And you need to find out where it started. So what we need to do is we need to use this, but we can't just use it straight up. What we need to say is, well, this is the sum. I'll talk about that in a second maybe. What I'm looking for is the sum from some random n, like I just said, maybe it's 9 cubed plus 11 cubed and so on, up to n plus 9. Now why n plus 9? Well, because I always go back to basics here. If you started at 1 and you wanted 10 numbers, this one would be a 10, and then it would be a 1 into 1 plus 9 is 10. So that's why I've added 9 there, not 10. If you went to 10, you'd add 11 things together. So just be careful to think that through a little bit. Now this is equal to, I can't use this very easily because it doesn't start at n equals 1, which is what we've just found. So let's start at n equals 1. To do that, we'll go from 1 up to this, but then we'll chop off the terms from 1 up to n minus 1, right? So imagine this was maybe a 10 and this was a 19. I'd go from 1 to 19 and then chop off from 1 to 9. And I think that will just get me from 10 to 19. So I think this works. Of course, now I've got everything set up in the right way. Starting at 1, I can just put in to the formula here. So if I'm going up to n plus 9, I just substitute in n plus 9s here. And if I'm going up to n minus 1, I just put n minus 1s in there. Now, it's really tempting to think that you can do something intelligent here, but you don't have to at all. You just expand everything out. You set it equal to this, because of course that's what the question says. You just expand everything out and then you just put it in a calculator. If it's only worth 4 marks, you're not being asked to do this in any intelligent, serious way. You just put it in a calculator. So just expand everything out, put it in a calculator, and it gets you the answer. Now n equals 6 is not the answer, and you know that for a couple of reasons. Mostly because 6 is not odd, so that can't be the first odd number that you use. What I'm saying is when n is 6, look back here, if n is 6, the first odd number I'm going to use is 2 times 6 minus 1, which is 11. So 11 will be the first odd number. And of course, please just spend 20 seconds typing into a calculator 11 cubed plus 13 cubed plus and so on up to doing 10 of them, and just verify that you get this answer, because I think that's definitely worth 30 seconds of your time, because it means you don't have to check through any of your working if it works, because it means you've got it right. So yeah, cool. N is 11 will be our answer. Question number 5. So we've got y equals arc cos of this. That's cool. Show that it has no stationary points. Now, the formula book does give me the derivative of arc cos. However, it gives me arc cos of x, not arc cos of a half x. So, and you actually get 2 marks on this question for differentiating this properly. The way that I did it was I just let u equal half x. It's unusual to do a substitution for a differentiation, but here we go. Let u equal a half x. And that means, of course, y equals arc cos of u. I can also say du by du as a half, by dx, sorry, as a half, of course, just differentiating this with respect to x, which means and then from here, dy by du is this with a u in it, of course, just literally using the book. But of course, I don't want dy by du, I want dy by dx, but I can use a bit of chain rule here. Dy by du times by du by dx must be dy by dx, thinking about just sort of cancelling these out. So let's just do this times this and we'll get dy by dx. It's just this with a 0.5 in here, of course, and a half timesing outside. And you got 2 marks for just getting this, and then 1 mark was for just saying, okay, well, stationary points need this to be 0, but and you can just bag this. I have looked through the mark scheme. You can just say, okay, well, if you times both sides by this denominator, you just get 1 equals 0, actually minus 1 equals 0, which is not the case. So there are no stationary points, and you can just say that. Good. The normal to see at the point where x is 1. So when x is 1, let's find dy by dx first. So when x is 1, we find dy by dx is this. It's just, of course, 1 minus a quarter, because 0.5 squared is a quarter, so that's 3 quarters. Root is root 3 over 2. Cancel the 2, you get minus 1 over root 3. And now we're looking at the normal. So the gradient of the normal is not this. The gradient of the normal is whatever you'd have to times by that to make minus 1, which I believe is just root 3, because root 3 times that would cancel, you get the minus 1 left over. So we have the gradient of the normal. We have x equals 1, so we can find the y coordinate just by putting 1 into there. So arc cos of a half. Think about yourself. What is cos of something is a half? What is that? Well, it's going to be pi over 3. You don't have to know that because, of course, you have a calculator, but it is nice to know that kind of thing. So it goes through 1 pi over 3, so let's just use y minus y1 equals mx minus x1 for this normal here. We get this. So that's the equation of the normal. And what else do we know about this? Well, we know that it crosses the x-axis at a. So when its y-coordinate is 0, its x-coordinate is a. So let's do that. Let's put that in and solve for a, and divide by root 3 and then add 1 to both sides, it looks like. We get a as that. And we also know it crosses the y-axis when x at the point b. So when we could just say maybe, I guess I've been a bit liberal calling this x-coordinate a. I guess it's calling the point a, not the actual point, but you know what I'm talking about. So when x, the other way around, when x is 0, we can just say y is b. We can solve for b and we get that b is this. Now be super careful here, because it's very easy to do this on autopilot and get a very wrong answer. you're looking for the triangle AOAB. Now, on the face of it, that seems really easy because A is just on the x-axis, B is on the y-axis. So it's just a half. It's just a triangle, and you just do half AB, right? You just do this length times a half. Except this length is actually negative because the triangle actually looks like this. B is down here somewhere, right? Because pi over 3 is like 1, and root 3 is like 1.7 going full engineer mode, and so that's a negative number. So you actually, when you're doing the area of this triangle, you want to take the magnitude of this, right? You don't want this negative number, you just want the length of this, which is just this the other way around. So it's a half. This is a positive number, so that's fine, but then this is negative. So sorry, this is negative, so you swap it around to get a positive, and then you just multiply this, expand out the brackets. You can put the half in here. In fact, no, what I have, I obviously always look at the answer. It says 1 over 54. How do I get a 1 over 54? Well, 1 over 2 times 1 over 27 is that. So I took out a 1 over 27 from all this, which of course requires to make a 27 there to make it cancel. I get this, put a 9 here, make it cancel, get this, and so on. And then you can collect this together, and that makes 1 over 54, and you actually end up with the answer that they want. And you can just maybe very clearly state what the numbers you've got are for your answer. Good, so that's question 5 done. Question number 6 then, all about polar coordinates, as we can see. We've got r is this, we've got exactly 4 points where the tangent is perpendicular to the initial line. Now, perpendicular to the initial line means dx by d theta is 0. So that's a result that you probably want to know. You can think it through though. You can think, okay, for any small change in theta, I want there to be no change in x, because of course if the thing's going vertically upwards even for a moment, when you change theta slightly, the x coordinate, you don't move left and right because you're going vertically upwards. So that's kind of how you can maybe justify that in your head if you're a little bit unsure. Of course x equals r cos theta, so we can kind of replace, so r you can say is x over cos theta maybe, times everything by cos theta, and now we can differentiate with respect to theta, and we can find dx by d theta, which we'll do here. Cos differentiates of course to minus sign. This, you can think of it as chain rule, 2 comes down to make a 4. The inside the bracket is just cos theta, which differentiates to sine theta with a minus, and then cos theta all squared goes down to cos theta to the power 1, which is just this. So we have this, we want that to be 0 of course, based on our work here. So we can factorize out a sine, of course. We know when sine of 0 is 0. Sorry, we know when sine of theta is 0. It's when theta is 0, as I just said, or when theta is pi. Not 2 pi, because we're not allowed to be 2 pi. Or of course this thing is 0. By the way, that means that we have 2 solutions, right? And we want 4 solutions. So we have 2 here, so we want this to have 2 solutions. So okay, that's just, I mean, the a's can just go away, of course, because we're assuming a isn't 0, they're positive constants. So that goes away. We can rearrange this for minus p over 4 as cos theta. Now if p is bigger than 4, cos theta won't have any solutions, because you'll have minus a number bigger than 1. So p has to be less than 4 here. And that's all I need to say. As long as it's less than 4, I'm going to get 2 solutions, because cos always has 2 solutions between 0 and 2 pi for any input aside from minus 1 itself, and minus 1 would be, and 1 of course as well, but that would require p to be 4, so that's why I'm saying p needs to be just less than 4, then we'll definitely have 2 solutions. And of course it's already told me that p needs to be greater than 2, so that gives me this, I think, as well here. Yeah, that gives me that. Good, sketch the curve. So we have 4 sort of places where the curve is vertical. We have one when theta is 0. Now when theta is 0, r is like, well, cos theta is 1, so r is ap plus 2. So it's some positive r over here. Now when theta is pi, which is of course in this direction, you have ap minus 2, I believe. Okay, well that might be just some other positive number going in this direction, I guess. Sure. So going this direction because theta is pi. And then we have 2 other solutions. Now we don't know where the value for that is, but maybe you'll have just seen graphs like this. Whenever you're asked to draw polar graphs like this, they're usually pretty similar. We know the graph needs to go through this area vertically. That's kind of what this is talking about. Just put 2 more points down. I put them down here and here. And then just say, okay, well, it's fairly clear how it's going to do this. It's going to go around here, it's going to be vertical there, and then come back again, vertical there, come back again, vertical there, and then come round again, like this. And the answer scheme gave a picture looked a bit like that. It usually looks a bit like that, so you should be, as long as you've seen these before, you should be okay to draw that, I guess. I don't really have any major advice for how to draw polar coordinates. Otherwise, I might make a separate video on that, but it seems to be the case that in these exams they always give you a very similar one to draw, so you should be okay either with vertical ones or with horizontal places that you know, and the graph always ends up looking the same in each case, or different in each case but the same as each case that isn't. So for this one it always looks a bit like this, is what I'm trying to say. Anyway, John digs a hole in his garden to make a pond, and he's going to dig roughly like this. Depth of the pond is 90, finds how long it would take if it filled. Okay, this is all about a volume question, right? We need to work out the volume of the pond, which of course means that we need to work out his pond has this cross-section area. So we need to work out this area, then we need to times it by the depth to find the volume, and then we need to divide it by how much the water goes in. We can deal with that later. So let's find the area of this first. Well, of course, that's going to be half integral of r squared between 0 and 2 pi, because we're going all the way around from 0 to 2 pi, and the formula for polar coordinates is just a half r squared. So we're going to take r, we're going to square it in here. Technically this 2, not technically at all, absolutely this 2 should be on the outside of the second bracket, otherwise there was no point in me doing the second bracket. This 2 should be there because I of course have to square the 20 and this here, or I should put a 2 here, it doesn't really matter, but you'll see what I do next and I'll hopefully talk through it. When the square goes here, 20 squared is 400, which can times by this half to make 200. And then I've just squared this to get here, but this 2 should totally be on the outside of the bracket, so apologies for that. But yeah, half integral between 0 and 2 pi of r squared, if that 2 was there, d theta. Of course, all of this is integral except for cos squared, which we can just use this formula for. Sine we can say is 1 minus cos, which makes this 2 cos squared, sorry, 1 minus cos squared. So that's 2 cos squared minus 1. You can notice you've got a 4 cos squared here, so if I double everything and add the 1 over here, I think I get this, which I can just put straight into there. The plus 2 can add to this 9 to make 11, and I think I can just get this integral, which is definitely doable just straight up. So this becomes 11 theta, this becomes 12 sine theta, because cos integrates to sine, and likewise the halves cancel there when you integrate. We just get this. Of course, when you put in 2 pi, this is quite nice, because sine of 2 pi and sine of 4 pi is 0, sine of 0 and sine of 2 times 0 is still 0. So the only thing that matters here is 11 times 2 pi, which is 22 pi, which is this. Which is times by the volume, so that's the area, right, of the thing. So times by the volume, times by 90, this is all in centimeters, so there's no units to change here. Times by 90 is this, which I think is, well, I've still got the pi here, I thought I was going to get rid of that, but liters is 1,000 centimeters cubed. I did not have to Google that, I totally did have to Google that, even though I've taught that to year 7s, I think in the past month. Still had to Google that, because I can never remember. But that's fine, I think, because that means we can just divide this by 1,000 to find how many litres it is, then actually use the pi to get this, and then divide by 50, and very roughly that's about 25 minutes, and we'll have our answer. State limitation of the model, you can always just write, what if this doesn't actually express the size of the pond very well? Like, you can basically just always write that and get the marks. In this particular case, you could have also said something about the fact that the depth might not be 90 all the way across. Like, yeah, sometimes it might be deeper in some places slightly, and not in others. I mean, there's lots of things you could say here, aren't there? Maybe this as well. You could talk about how the rate might not actually be constant, 50 litres per minute all the time, maybe. I don't know. It's up to you. Question number 7 then. So we've got another integral. This is going to be a volume of revolution this time though. So we've got arc shine here to deal with. We can of course get out the formula book. I mean, firstly we're going to have to deal with this here. So this is the point alpha beta. So y is beta, but beta is this. So I'm going to substitute that into there and solve this for alpha. Of course, you can do shine of both sides to deal with this. I think first, actually, I said that using power laws of logs, this is 3 to the power half, which is root 3, then do shine of that. It's totally possible to use this formula from the formula book at this point to solve for alpha. It's probably easier to put shine on the other side and just use the exponential definition of shine from here. So this is going to be, so shine of x is equal to e to the x minus e to the minus x all over 2. So we can put this in as x here. Of course, e and log cancel here to just get you a root 3. This minus 1 has to go there first to get a root 3 to the power minus 1, and then the e and the log cancel to get you this. This is just 1 over root 3. You can times top and bottom here by root 3 to get 2 root 3 on the bottom, and 3 minus root 3 over 3 on the top. Sorry, 1 over root 3 on the top. Sorry, 1 over, what am I even talking about? Times this by root 3, and you get 3, and then here you get just 1, right? 1 over root 3 times root 3 is just 1, of course, you idiot. So yeah, root 3 over 3. Am I taking crazy pills? Yeah, no, I'm not. I'm fine. Yeah, it is definitely 1. I mean, I am. This is going to be 2 over 2 root 3, which is obviously just going to be 1 over root 3. I probably did too much work there, and I definitely did too much waffling. But anyway, we have this. Then we have the finite region R, which is this, and we have to integrate this around the y-axis. That's going to be pi, the integral between 0 and 2 pi. Sorry, between 0 and beta. Talking about polar coordinates still. So it's going to be pi times the integral from 0 to beta of x squared dy. Oh, sorry, going backwards. X squared dy, because we're going around this way. Now beta we already knew is this, x squared. Now here we can say x is equal to sine y. We can square that. Now integrating sine squared is not that fun, but we've seen this before, right? It's the same as sine and cos, right? You just use the double angle identities. So from here we can say maybe that, okay, well if we combine a couple of things in here, cos is clearly equal to 1 plus sine squared, so we can replace that with a 1 plus sine squared, which makes a 1 plus 2 sine squared, and then we can rearrange this a little bit to be cos 2x minus 1 all over 2. And that'll be our x squared. We can put that into there. Of course, that's very integrable. I've moved the half outside just because, of course, I have. You can integrate this. Cos integrates straight to sine with a half in front, of course, because of that 2. 1 integrates to y. Put these two limits in. And yeah, I think it's fairly self-explanatory from here. You can, of course, times all the halves together to make this. I'm not 100% sure whether or not what you're seeing on the screen here would get you full marks. I'm inclined to believe it wouldn't. I think I could argue that maybe this is exact value already, but the marks team wanted you to deal with the sine, which of course is probably a very safe thing for you to do. You've got an hour and a half, you may as well deal with this kind of thing. We've already seen sine is e to the x minus e to the minus x over 2, so let's replace that there and do a very similar thing to what we did before, whereby this cancels immediately for a 3, this makes a 3 to the power minus 1, and then cancels, which is 1/3 here, and then this makes 8/3 over 2 is 8/6, which is 4/3. And we'll have an answer that I think is a bit nicer. So yeah, I think you should probably just leave it like that. Anyway, I think that's the whole question. Good, yeah. So question number 8. I think there are 9 questions here from memory. So we have point P is one vertex regular polygon in Argand diagram. Center of pentagon is at the origin. So we have one point on this pentagon, and we want to know where all of the other points are. And this is actually, when people ask, oh, complex numbers, are they really used in real life? This is the example that I like to use. Is like if you were trying to draw a pentagon and you knew one, and you just put down one point somewhere, how would you know where to put all the other points to make an absolutely perfect pentagon centered around a point? And I mean, it feels like a dumb example, but you can imagine how like a computer program would need to, when you draw a pentagon, even using PowerPoint, like I have, you can imagine how a computer program would need to use that. And yeah, the easiest way to do it is using complex numbers, right? You put the coordinate that you've got in terms of complex numbers, and then you multiply by just the fifth roots of unity. Pentagon has 5 sides, of course, so we're going to use the fifth roots. I know that's the first fifth root of unity, aside from 1, of course, because if I raise this to the power 5, I get the 5 times the over 5 cancel, and you get e to the 2i pi, which is of course just 1 because you're going all the way around the circle, so it's just 1. So I know that's the first fifth root. You can just take this, you can put it in exponential form. Of course, this is just, I mean, it's got modulus 2 root 6, of course, hasn't it? 6 squared plus 6 squared rooted. And it's got argument tan inverse of 6 over 6. I mean, that's just a line gradient 1, so it's pi over 4, right? So that's this point in exponential form, and just times this point by that root there. And of course the modulus stays as it is, and then this is just a quarter plus 2/5, which is 5 plus 8, which is 13 over 20, and we have this. And then just do it again. Just take this point, so that's our second point on the pentagon. Take it and times it by this again. You could times the original point by the next root of unity, but I think it's easier just to do this one by one. Just do this one times this next, and you get this answer. Again, just by adding these two together, then take this answer, times it by this again, and just do it until you have 4 of them. Because when you have 4 of them, you have 1, 2, 3, 4, and then the 5th point is there, and we have 5 points here, all in the form this, and that will be my answer there. Next question is completely different. It's about an Argand diagram with this. This is a circle centered to I radius 2. It's actually a disk, isn't it, technically, because we're less than or equal to 2. This is 2 half lines originating at the origin, gradient a quarter pi, from angle a quarter pi to a third pi. This makes gradient 1, of course, as I've already talked about here. Same thing. So of course we have a disk centered to I radius 2, so it goes down to the origin here. We have a line that's gradient 1 this way, and a line that's a bit steeper this way. And the area between the 2 lines and in the disk is going to be this area here. And now we need to find the actual area of that. Now the easiest way to do this is using polar coordinates again. So we have, and using that area. So let's find the area of this, the equation of the circle in polar coordinates. Now some of you might just be able to write down what that is, but just for those who are a little bit less sure, the equation of this in Cartesian form is clearly just x squared plus y minus 2 squared equals 2 squared, because the center is at 2 here, and the radius is 2, as we've said, so that's 2 squared there. And now you know in polar coordinates that x equals r cos theta and y equals r sin theta, so you can just put those in, and then you can square these things out. And of course this thing here, you can factorize r squared into cos squared plus sin squared, which is just 1, so you just get r squared, and then these 4's cancel, and you get this, which you can factorize out of 4, from an r from. R can't equal 0, because that's a radius, I mean, r can equal 0, right, I guess. But more interestingly, when this equals 0, you have r equals 4 sine theta, which will be the equation of this circle all the way around here. Cool. R equals 0 just gets you the initial point here, I guess, at the origin. But the rest of it is described via this. And of course, if r equals 4 sine theta, that means the area here is going to be half, as we saw before, the integral between this line and this line, which is just this and this, of r squared. So we can just put that down. We'll square this out for 16 sine squared theta. 16 times half is 8. I've decided to donate 2 of them to there because, of course, I think this is the 3rd time we've done this. We have to replace sine squared so we can integrate it. So I use this, which I can turn into this by saying that's 1 minus sine squared, and then I can move the 1 over, divide by 2, except if I've got the 2 there, I don't have to divide by 2. I can just immediately do that, which is why I did that. Integrate that for this, and now it's very straightforward from here, isn't it? You just put the numbers in, and you type it all in. You could know these off the top of your head if you wanted to. Otherwise, just type it all in, and you'll eventually get your answer. Good. Question number 9 then. So this, I guess, has come up when I didn't really want to. I don't think I'm even going to use it either. I think I was thinking about using it and then stopped. But maybe I left it there because I was going to discuss it. Given this here, so this is a geometric series, right? It's got ratio z, it's got initial term a, so the sum is going to be a over 1 minus r, as long as this is the case, which is that it is. R is z, a is 1, so we just end up with this. And that'll be our mark. S I've just called this sum, so S is the sum. Given z is actually this, so I've written this as this because I was thinking about using it. I don't think I'm actually going to, though. Use the answer to part A and De Moivre's theorem to prove this thing here. Now, okay, what we need to do here is we need to write this with this first. You don't have to do it first, but I did it first. So 1 plus z is this, and then plus z squared is this, and then z cubed is this. And now from De Moivre's theorem, you can, obviously this is all fine, the square out here makes this into a quarter, and then this thing squared. But De Moivre's theorem, as we've already seen, just means you can put 2's in here. Rather than doing any kind of binomial, you can just put 2's in here, and then for this one you can do a half cubed, which is an 1/8, and then put the 3's in there, so that's fine. So that's one way of describing S. The other way to describe S is via this. So we put Z into there, and now there's expand that out. And like I said, it's possible to use this instead, but I decided just to use this. After I typed this all up, you'll see why I didn't bother to do that again, because I've done all the work. You want to rationalize this. So times it all by this. So just change the bit with the, not rationalize, I guess realize, change the bit with the I here. So make that into a plus and times by Tom button that. Now, of course, 1 times this is just all this. Now this is a bit annoying. It's 1 times all these things, but then notice how 1 times this makes minus half cos theta, and then this times this makes minus another half cos theta, that's minus 1 cos theta. So you can put those 2 things together straight away. And then of course some things cancel, like 1 times this, and then this times this. Well, one's got a positive, one's got a negative, so that'll cancel. And likewise this, and then this will also cancel. So we're just actually going to be left with the 1 times the 1, the cross terms that you get from these, which is minus cos theta. You'll have a quarter cos squared from here, and you'll also have a quarter sine squared from here. The i's, of course, when they square, make that into positive. But a quarter cos squared plus a quarter sine squared is just plus a quarter. So we can put that together, and we get this. And then we can times top and bottom here by 5 to get this, and of course this is looking great, and we have some good work here. And now of course that's another way to describe S. So we have this is equal to this because they both describe S. I split this out, by the way, into its real part and its imaginary part, and you'll see why. Because of course it's going all the way back to question number 1, I guess, when we were comparing things that had x. I think it was actually question 2, wasn't it? When we were comparing things that had x's and things that didn't. From here we can compare things that have i's in them and things that don't. So over here the imaginary part is this bit, the 2 sine theta over 5 minus 4 cos theta, and the imaginary part over here is a half sine theta plus a quarter sine 2 theta plus an 1/8 sine 3 theta, and so on, which I think gives us exactly what they wanted us to have. Good. Show that this cannot be purely imaginary. So show that this thing here, the sum S, cannot be imaginary. Now using this bit is the easiest bit to do, I think. So show that this cannot be purely imaginary. Well, for it to be purely imaginary, we would need this bit to be 0. But of course, if we times both sides by this denominator, we just get this is 0, and I don't think this can be. Add 2 cos theta, you divide by 2, you get cos theta equals 2, and that doesn't have any real solutions at all. So we have no real thetas that will do that, and so there's no actual way for S to be purely imaginary based on that. And I think that's the entire paper. I thought it was a really tough one, so thank you for watching, and I'll see you next time.